Hi, welcome to our 28th lecture in Graduate Combinatorics. Today we'll continue discussing trees, and more precisely, we'll talk about some algorithms on trees. So we'll discuss breadth first search, depth first search, and Kruskal algorithm. They all involve trees. So first, to start describing these algorithms, we need the notion of a Rooty tree. So a Rooty tree is an order pair T and R, where T is a tree and R is a vertex of T called root. Okay, so basically a Rooty tree is a tree with a specific vertex of it called a root. Now, if we have so we have this special vertex, which is the root. So in that situation, we can define the notion of a level. So if we have in a TR Rooty tree, the level of a vertex X, so if you have X, a vertex of the tree, the level of X, which is, let's say, denoted by L of X, is the distance from R to X. So this is the length of the shortest path between R and X, and because it's a tree, this is a unique path, so it's the length of the Rx path. So let's do some examples to understand better what we're talking about. So let's say we have, so in the picture I have a tree TA, where A is this vertex. It's adjacent to the vertices B, C, and D. So this is a Rooty tree, which is rooted at the vertex A. And it's common to draw the root on the top and then its neighbors below it at the same level and so on. In some fields, this orientation is reversed and the root is at the bottom and its neighbors are up, but I'll just draw the root on the top. I can have a similar example. Let's say here, if I root this tree at the vertex C, then the tree looks, so it's C, then you have A, and then you have B and D. So you see the difference between TA and TC. And for the tree on the left, the level of the root, so the level of the root A is 0, because that's the distance from A to A, and the level of these vertices L, B, C, and D is 1. Okay. Now, for the tree on the right, the level of C is 0, because that's a root. The level of A is 1, and the level of B and D equal 2. Okay. All right. So that's a Rooty tree. I think it's pretty clear. And now, if we have a Rooty tree, so if we're given a TR, a Rooty tree, I want to talk about what are called the breadth first traversal sequence. So breadth first traversal, and I'll do it kind of in parallel with depth first. So breadth first is abbreviated usually BF, so BF traversal, and depth first is DF traversal. These are two of the most commonly used ways of traversing a tree. And so let's do our example as before. Let's take, or maybe I'll do a different one. Let me do this tree that I have in the notes. Let's say we have a tree here with A, B, C, D. Maybe I'll give a different example. And I do here E and F, and I have C adjacent to G. Okay, so let's use this this example on the top right. T rooted at A. That's our tree. Okay. Now in the breadth first search traversal, it's a listing starting from the root. And it's essentially you list the, so you start with the root and you list, so let me put it here. It's essentially a list, order list of the vertices according to their levels. So in this situation, I have the first level 0 is A. So this is the level, this is level 0. And then you have a choice, so you can put some order on the vertices. In this case, let's put lexicographic order. And then you list the vertices that are level 1, which are B, C, D. So it could be done theoretically in 6 ways, but let's just do it B, C, D. So each of them have level 1. And then there's nothing coming down from vertex B, but from vertex C you have, because this is the first one that comes in the list of levels 1, you have a G that is at level 2. And then again for D, you have 2 choices, EF or FE. So let's say EF. So this is level 2. Okay, so this is the breadth first traversal for this tree. Now the depth first traversal is kind of you know, imagine being in a forest, and the breadth first traversal is kind of like the more cautious way of traversing the tree. You just do small steps. You know, you start at the point, you go to its neighbors, and you come back, and then you go to the neighbors and so on. The depth first search traversal is you go as far as you can go. And one way of thinking about it, think about this, the edges of this tree as being a fence, and you start at the root. Imagine walking down, and you keep the wall on your left, and you walk around the wall. So as you're going down, you write down the vertex that you. So here, let me write a brief description. So imagine the edges wall. Start at the root. Keep on your left. And write down the vertices that that you see the first time, when you see them at the first time. So you start at A, and then you're going down on the top, and you see the vertex B there. And then you turn around, and you come back at A, and you go down now on C, and you're going to go CE and come back around. So release now C and E. And then you go start again from A, you go down D, E, D, no, this is G here, sorry. This is G. Then you go D, E, and then you come back and you get F at the end. Okay, so this is the, so you see the levels here are not as organized as is in the previous case. They actually increase, and then they go back up and decrease and so on. Okay. So let's do one more example. So if we take the tree that we had earlier, this one, just a simple tree, C, A, B, D, then if you do the breadth first traversal, you start at C, then you go at A, and then you have B and D. So that's what it is. And in this case, actually, the what is the depth first traversal is pretty much it's the same in this case, because you go as far as you can go. C, A, B, D. But in general, as you see on the tree on the top, these traversals are quite different. Okay. Now, I need one more definition. Maybe I'll squeeze it here. So if we have a TR, a Rooty tree, and we have a vertex in the tree, and the vertex is not the root, we'll scan that in, we'll see why that in a second, then we can define the parent of X, which is denoted by P of X, is the neighbor of X on the unique Rx path. So if you go from the root and you go to the vertex X, as the parent, you write down the vertex that you see just before you reach X. So if we look at the example here on the tree, this small tree here, so again, the parent is not defined for the root, but the parent of A is C, and the parent of B and the parent of D is A, so that's pretty clear. And on the tree here on the top, you can see if the parent, let's say, of F is D. So this is pretty clear, I think, this notion of a parent. Now, why is this notion useful? Well, if we have this parent function, that gives us the whole information about the tree. And this is summarizing the following proposition. Let T be a Rooty tree, then the edge set of T consists of all the pairs X parent of X for X not equal to R. So if you give me any tree, so we have this tree rooted at here. Let's call this vertex R, and I have here A, B, C, D, E, G, H, I. Then if you ignore the root and you look at every other vertex, then that's what the edges of the tree are going to be. It's going to be A parent of A, which is the edge AR, and that's the one here. And then similarly, you get B parent of B, which is B and A, and so on. Okay. And yeah, these are all the edges of the tree. Now, okay, so what is, now we are going to talk about the breadth first search and the depth first search. And so these are ways of traversing a graph and producing a spanning tree of that graph. So the graph is supposed to be connected. So in our example, let's take an example of a graph. So I have this example in the notes, small graph. So this way, and we have A, B, C, D. Okay, so this graph is connected and it has cycles. So it will have several spanning trees. And what we want to do is we pick a vertex. Let's say we pick the vertex A, and we want to find a spanning tree of this graph gamma. So you want to produce a Rooty tree. So maybe the more general setting is we have a vertex R in the vertex of gamma, and we're going to produce TR, and T is the spanning tree of gamma rooted at R. And this is a breadth first search spanning tree. So basically it will contain again the start with the root, which is let's say A, then it will list the neighbors of A in the tree, in the graph gamma, so the ones that are at distance 1, then it will go below it and you will list the ones that are at distance 2, and so on. Okay, so how does it work? So this is the breadth first search tree. So to do that, you need what data structure, which is called a queue. So this is an example of a data structure. You can think of it as a ordered list. So you can think of it as an ordered list in which we keep the vertices, and it has the property that it's similarly as a queue that you have in the in your usual when you're waiting for in line. So let's say let's say you have it has two. So if we have the queue of the form A, B, C, the one on the left, this is called the head, and this is at the end, it's called the tail. And when you insert an element, you insert it at the tail. So the tail, and when you remove it from the head. Okay, so let me give you some example here. So let's say we have A, B, C. This is our queue. That's the current state of it. And then we want to insert D, and then the queue becomes, so let's say Q is this, then Q now is going to be A, B, C, D. You see Q goes at the end, and then you want to remove an element from the queue. Q, remove the head of Q, then Q becomes B, C, D. And then if you want to, you could insert A back if you want, insert A in Q, then the Q becomes B, C, D, A. Okay. So this is an example of a data structure which is called first. It's abbreviated FIFO, so it's first in, first out. Okay. So now let me describe to you the algorithm to create this, so we have given a graph gamma connected, and let's say R is a vertex of gamma. So that's our input. Okay. And so what does the algorithm do? So you start with a Q, and you initialize it with the root R, and then you want to calculate this level. So the level of R is 0. Okay, and you mark R as visited. So the vertex R has been visited. Okay, and now there's a loop. So while Q is not empty, we take X, let X be the head of Q. So in the first step, X is just the root, okay? And now we have a if conditional. If X has a neighbor Y that has not been visited, then what do we do? Different colors. Then you mark Y as visited. You assign the parent of Y, you assign it to be X, and the level of Y is you assign it to be the level of X plus 1. Okay, so that's the loop here. So this is if X has a neighbor that has not been visited, then you do this. Otherwise, else here, else basically we visited X, so all the neighbors of X have been visited. So in that case, X can be removed from the queue. Else remove X from queue. Okay, so this is you end the loop here, and if, and then you end while here and while. And what this gives us, so the output is going to be a Rooty Tree TR. And we get a parent function, P, parent function, that tells us all the edges in this tree, and L, the level function, which tells us all the distances from the root to the vertices of the tree. Okay. So let's do this algorithm for the tree that I described earlier. So we have this tree here. Oh, this graph. So we have A, B, C, D, E, F. So this is our graph gamma. And our root is, let's say, A. Okay. So how does the algorithm proceed? Well, you start with the, so I'll just show the evolution of the queue and the levels of it. So you start with the queue to be A. And so I'll just draw the vertices as they're visited, make them blue. So that's the initial step. And then you enter the while loop. And we have A is the head of Q. And then, yeah, A has neighbors that have not been visited, and you pick the first one, the neighbors. So again, you can choose B first or D first, but let's work lexicographically. So let's say B is the first neighbor of, okay, I think there's something else that I miss here. So you have, I did. So you mark Y is visited here, you put the parent, the level is up, and then you add what the last thing, you add y to q. That's a very important part here. You add y to q. Okay. So here b is the first. What do we have? We have, so the level of a is 0. B is the first neighbor of a. So we have parent. We assign parent of b is going to be a. Level of b is going to be 1 because it's a level of a plus 1. And then the q changes, and the q changes to become ab. Okay, and this vertex has been visited. Then in the same queue with a, like a is ahead. Does it have a neighbor that hasn't been visited? Yes, this is the D is the neighbor. And in this situation, we do the same thing. We do P of D equals A, level of D equals 1. And now the Q becomes A, B, D. Okay. And then when you try to run it one more time, you know, all the neighbors, of A have been visited. So we're done. And what that means is that we remove A from Q. So now it means that Q becomes B and D. And we go back in the while loop. And then when you go back in the while loop, B is the head of the Q. And we say, okay, does it have neighbors that, yes, the first neighbor will be C. So we visit now C. And what do we assign to C? The parent of C is B. The level of C is the level of B plus 1. So that's going to be 2. And we add, so the Q becomes now B, D, C. And then does B have any other neighbors that haven't been visited? Yes, that's E. Do the same thing. P of E is B, and the level of B is 2, and the Q becomes B, D, C, E. Okay, so this. And then we are done because all the neighbors have been of B have been visited. So you remove B, and so that gives us the Q. Let me go here to the top. The Q becomes DCE. And you take D, all its neighbors have been visited, so it means you can take it out from the Q, so the Q becomes C and E. Does C have any neighbors that haven't been visited? Yes, that's F. And then with F, you do P of F. The parent of F is C, F, and the level of F is 3. And then pretty much after that, you remove C and you remove E. Okay, so what does this produce? So we have, and now what we have is, it gives us the levels. So let me write the levels here. Level of A is 0. The level of D and B are 1. C and E are 2, and the level of F is 3. And it produces the parent function, and the parent function are these edges between, so you have these edges. Okay. So intuitively speaking, is like you're hanging out the graph from the vertex A, and you've got now this, so you have A here, you have B, you have D, and then you have C, and you have E, and you have F. Okay. And so what it does, this algorithm, So proposition, what this does is, so you have, if you have gamma connected graph, and R a vertex of gamma, and denote by R the rooted BFS tree of gamma. So number one, what it produces is that it gives you the distances from the vertex, any vertex to the root, but not just in the tree, but in the graph. So the level, so let me write it this way. For any x in V, the level of x equals actually the distance in the graph gamma from the root to x. You know that the level of x is the distance in the tree from R to x, but it's actually the distance in the graph. And the second part is that any edge of gamma connects any edge of not of gamma of T connects two vertices whose levels differ by 1. So essentially, the edges in the tree are going to be of the form x parent of x, and by the way we assign the parent here, all throughout, the difference in the levels is always going to be 1. Okay, so that's not so difficult. And the first part is not difficult. You can prove it by induction on the number of vertices. So the one thing you can use this breadth first search, you can use it to find if you pick a vertex and you want to find the distances in the graph, so the lengths of the shortest path from that vertex to any other vertex in the graph, you can do the breadth first search algorithm, and that will give you the tree, and the levels that you obtain, those are the distances that you want. Another application of it, so that's one application. Another application of it, you can use it to check if a graph gamma is bipartite, because when you do the when you do this breadth first search, you have these levels. So you have level 0A, and then the neighbors are at level 1, and then the neighbors of the neighbors are level 2, and so on, level 3. And if a graph is bipartite, the partition into vertices at even levels, and then in one part, and then the vertices at odd levels in the other part, that would be a partition into two independent sets. So if you're looking for odd cycles, all you have to look is to check if there are any edges that join vertices at the same level. And in our situation, we can find this edge between C and E, which joins two vertices at the same level, and that guarantees us that we have some odd cycle, in this case, a triangle. If we had done the tree rooted at B, you could have found this triangle much faster. But in this case, yeah, you have to go deeper, because we're looking at the tree rooted at A to find that odd cycle. Okay. So these are some applications. Now, let's do now the other type of traversal, which is called the depth first search tree. Okay. And how does it work? So in this situation, So let's use the same. So we'll use I guess the same example, but for the depth first search, we'll use a data structure which is called a stack. And this one you can think of it as I won't write it like that, but you can think of it as, if you think about A, B, C, you can think of a stack A, B, C. So C is at the bottom and A is at the top. And when you remove, so the top is the head. So you remove an element, the head of the stack, let's say S, then the stack becomes B, C. Okay, so when you remove, yeah, that's clear what happens. So you remove from the head, but when you insert, you also insert into S, insert, let's say, a new element, let's say D in S. Then if this is S, B, and C, and you insert D, you also insert D at the top. So you have this. So this is a type of data structure that is abbreviated LIFO. So it's last in, first out. And the name stack is the analogy of a stack of plates. You always insert at the top and you also remove from the top. So our graph is before. Let's do it this way. This is D, E, F, and the breadth for search tree was just draw it, just the edges of it. A, B, C, D, F. Okay, now for the depth first search algorithm and the depth first search tree, the same situation. We have the same input. We have gamma. We have a connected graph. We have a vertex in it. And sorry. And then the output will be a tree T, or so a rooted spanning tree of gamma, and a parent function P, a parent function, which tells us all the edges in the tree. Okay. So how does what does the algorithm do? So you start with a stack now S, which is R, and again you mark R as visited. It's very similar to the previous one, but you just use a different data structure. So while S is not empty, we take X to be the, I guess the head of the stack is called the top. Let X be the top of S. The same question as before. If X has a neighbor Y, neighbor Y that has not been visited, then what do? Mark visit Y, mark Y as visited. Do P, parent of Y is X. That's how we got there. And we add Y to S. So you see here the level, we don't do the level because it doesn't keep track of the distances. And then this is and it's if you add y to s, and then else you remove x from s and y. Okay, so this is the algorithm, and let's see how it goes on the. So let's see how it goes on this tree here. Okay, so I will do here the depth first search. So you start, let's say it's at the root A, and we'll keep track below by so the stack is initially A, and then A is visited. You go to the first vertex. A is the top of the stack. It has a neighbor that hasn't been visited. That's the neighbor B, and now the stack becomes BA. Okay, so S becomes BA, and then we visit B. So we visit B, we keep track of the parent of B is A. So that's an edge of our tree, and we added B. Then the stack is not empty. So we're back to the first step into the while loop. So we take X to be the top of the stack. That's going to be B. Does B have a neighbor? Well, the neighbor A has been already visited, so we don't go there. But B has a neighbor that hasn't been visited, that's C. So the stack becomes BAC. So the tree goes there. So maybe I'll keep, and then we keep, stay here. The stack is not BAC, it's going to be, that's the whole key, is going to be CBA, that's the stack. And we go to C. The top of the stack is C. So does it have a neighbor? Yes, it's E. So it becomes ECBA. So it goes here. And then from there, it's going to become DECBA, because that's the neighbor of E. And now we are at D as the top of the stack. All its neighbors have been visited. The neighbors of D are A and E, so we can delete D. Then the head of the stack is now E, and then you have to go to F. So you put F, E, C, P, A, and so that's the tree that we get. And now you delete F, and then you're going to have E, C, P, A. You delete E, you delete C, you delete B until it's empty. So the trees are quite different. So you see, you get the blue tree for the breadth first search, and you get the purple tree for the depth first search. And so what does the depth first search give you? So I gave you earlier the definition of a parent. So we have the definition of a parent. We can extend the definition to the notion of ancestor and descendant. So if you have again a TR Rooty Tree, so if you have so a vertex X is an ancestor of Y if X is contained in the RY path. Okay, so a parent is an example of an ancestor, but you can have the parent of the parent and so on. That's also an ancestor. And a descendant, it's the other way around. So in that case, if X is contained in the RY path, then X is an ancestor of Y. And you can say that Y is a descendant of X. So if we have a tree here, this purple tree, you could draw it like this. A, B, C, D, E, F. If you want to draw it rooted at A, it's kind of A, B, C, E, D, F. So if you want to figure out the ancestors of D, the ancestors of D are everything on the path from D all the way up to A. So D itself, E, C, B, A. And if you want to do descendants of C, are everything going down from C. So C, E, D, F. And two vertices, you can say they're related. Two vertices are related. In this tree TR, if one is the descendant of the other, is a descendant. So when you do the depth first search, what you are going to get is the following. So if we have, as before, let gamma be a connected graph and R a vertex of V, and then denote by TR the DFS Rooty Tree of gamma. And what you get is that these are the following properties. The endpoints of any edge, any edge of gamma are related in T. And two, you get the following property is that the deletion of the root disconnects the graph if and only if R, so the root R has at least two children in T. So back to our example. Okay. So you see, it's the first part, the endpoints of any edge of gamma are related in T. So if that edge is a purple edge, then it's clear that those endpoints are related in T by the definition. But this is also true for any other edge. So if you take, for example, the edge AD, the edge BC, or the edge CF, in each situation, for the edge AD, A is the ancestor of D. For the edge BC, B is the ancestor of E. And for the edge CF, C is the ancestor of F. And the other part is that the deletion, you see in this case, the root is A. and it has degree 1 in the spanning tree, and if you delete A, you do not disconnect the graph. And so try, for example, if I give you a graph like this. So try doing a depth first search tree rooted at this vertex here, and see what the degree of that vertex is in the tree. So I'll leave this this proposition as an exercise for you guys to think about. I'm out of time, so I will do Kruskal algorithm next time.